Ken's been working here a number of years, professor, and he was interim provost a few years ago and went back into teaching, and now he's the interim provost again as of July 1st. So let's have a round for Ken Tabbutt. And he's going to present from the geologist perspective about the Alberta oil sands. So just let you take over.
Thanks,
Thank you.
Thank you. So I was invited here, Cindy, 4 or 5 years ago. I talked about this, and what I found was you guys have lots of questions, and so I welcome you to ask questions as I talk. And in fact, I didn't get through my talk because there were so many questions. So, like Cindy said, I'm a geologist. I'm not a epidemiologist, and I'm not an expert on environmental policy. So I can talk to you, and I will talk to you about fossil fuels and sort of the setting of the Alberta or the Athabasca Tar Sands. And I mean, it's a really interesting subject, both in terms of sort of just the geology, but also the environmental impact and the cultural impacts that go along with extracting that resource. So I'm going to start out just talking generally about fossil fuels, what they are, how they form. So fossil fuels is sort of a family name, and it refers to sort of any plant remains that have been trapped in sediments for a long period of time, and now we can use it as a fuel source. And the really important thing to think about in this talk today is fossil fuels, their name implies it, have been locked up in the earth for millions and millions of years. And when we talk about the Athabasca Tar Sands, we're talking about carbon that's been locked up in the rock for over 100 million years. So it's really important to keep that in mind in terms of when we start talking about global climate change and combustion of fossil fuels and what that's doing to our atmosphere. So yeah, in the case of the Athabasca carbon, it originally was trapped by plants over 140 million years ago. And so for the past 140 million years, it has been underground and sequestered away. And so now when we extract that fossil fuel and we combust it, it's going into the atmosphere and increasing the CO2. But not only is it increasing the CO2 in the atmosphere, but it's releasing carbon that's been sort of in storage for millions and millions of years. The type of sediment, the kind of organic matter, and the process of alteration and the amount of time, pressure and temperature the rocks have been subject to really determine what type of fossil fuels you end up with. And the most common is coal. And so coal is a combustible sedimentary rock. In fact, I brought a piece of coal, and I'll pass it around. You can take a look at it. There's coal being mined throughout the world. The black spots are sort of places where coal occurs right now throughout the world. We used to have a coal mine just south of here in Centralia that is no longer active, but now we get most of our coal. You can see in the sort of in the Great Plains, the western part of the Great Plains, there's a lot of black. Those are coal deposits, and that's mainly where, at least in the west, we're getting our coal. So there's an awful lot of talk about coal trains and bringing coal from mainly from Wyoming and the Powder River Basin. So I'll pass this around. Take a look at a piece of coal. So coal is really, like I said, it's the most abundant fossil fuel. It's also made up of plants and plant material that has been compacted, heated, turned to rock, but it's a solid. So it's a fossil fuel that doesn't tend to migrate around underground. It's usually formed in, when the coal forms or when the plants that form the coal form, it was usually in marshy areas, in estuaries, or in deltas, or in swamps. And over a long period of time, that material, the plants live, it dies, it accumulates, and then over millions of years it compacts into coal. So that's the most abundant fossil fuel. Then the one we hear probably the most about is just petroleum. And I'll use petroleum and oil sort of interchangeably. And so petroleum, unlike coal, is a liquid, or it can move like a liquid. And it's produced primarily from plants as well, but instead of large vascular plants, it's usually microscopic plankton and algae that once grew in oceans, and as it died, it accumulated on the bottom of oceans, and that's sort of the source of the carbon for oil. And again, there's sort of a map showing where the major oil reserves are in the world, and you can see that there's some in the North America, there's quite a bit in the Middle East, in Russia, Northern South America. And again, because oil's a liquid and it tends to be fairly low density, oil tends to want to migrate to the surface. So we'll talk about why it doesn't always migrate to the surface. And then the last fossil fuel, which is related to both coal and oil, is natural gas. So primarily methane. And so if you have coal deposits, you often have methane associated with coal deposits. And then if you're mining or if you're extracting petroleum, there's usually natural gas mixed with the petroleum as well. Natural gas, like the name indicates, is a gas, so it's very difficult to transport around. So oftentimes, especially in more remote areas, it's just flared off. In other words, it's burnt because it's just too costly to try to ship it to some place that could use the natural gas. So there's a picture of an oil rig that is really trying to produce oil. It's got the byproduct of natural gas, and it's just flaring it off. It's just burning it as a byproduct. But you can also see sort of the areas in the world where there are large reserves of natural gas. Usually it's sort of in the same areas that you get coal or oil. Let's keep going. So oil shales and oil, I'm gonna sort of go back and forth between oil shales and oil sands because they're sort of the same thing. It's just a matter of whether it's sand-sized particles or mud-sized particles you find it in. You can see that they're found throughout the world as well. And Alberta has a huge quantity. And so that's what the case study focuses on. That's what we'll primarily be talking about today. But you can see in the map that it's not just in Alberta, but there are places in South America, in Russia, and other places where you get these oil shales. And the oil shales are a little different because the oil isn't as mobile. In other words, you can't just put a well down and pump the oil out because it's sort of trapped in the rock. And so you have to do some more complicated procedures to get that fossil fuel out. And I actually brought a sample of oil sand from the McMurray Formation. This is the Athabasca Bituminous Sands. So I'll pass it around if you want. You can unscrew it, smell it. It smells like oil. It smells like asphalt. It's sort of crumbly, but it's right out of Alberta. Anyone, any questions at all? We're doing okay? Okay. Yes?
Just one about where these deposits are. Is it shown just on the land
And if it's deep, then you have to go underground to get it. But this is just showing sort of the distribution in the world, not how deep it is. But it is underground, most of it. Yeah, question?
You show them burning that natural gas.
Yeah.
Is that just kind of a waste of
Yeah.
natural gas that they can harness and produce?
It's just because it's too expensive for the company to either build a pipeline to pipe it out or condense it into liquid natural gas. So they've decided that they have to get rid of it, and so it's easier just to burn it off. And you see that a lot when you look at oil wells. If they're looking for oil and they're getting gas, they tend to flare it. It's a waste, no doubt about it. All right. So, why are fossil fuels important? I mean, the main reason is that the world is addicted to oil, or fossil fuel, I should say, not just oil. Our modern society is built to depend on fossil fuel as an energy source. And it's really difficult to shift energy sources. So this is sort of a diagram of the global energy demands up to today, and also the projected demands for energy in the future. And you can see that whether it's coal, oil, or gas, all of those demands are going to increase. They have been increasing, and they're probably going to continue to increase in the future. It's nice to, I mean, the last time I came and talked to you, this is only 4 or 5 years ago, there wasn't as much emphasis on looking at alternate energy sources. And today, it seems like there's a little bit more impetus in terms of looking at non-fossil fuel sources. So hopefully, maybe that projection won't be quite as steep. Maybe there's some other sources that might replace some of the fossil fuel that we're using. But right now, I mean, we drive cars. Most of the energy that we use is coming from fossil fuel. And so that's why there's a huge demand to get it. So when you think about petroleum, you have to have several geological processes working for you in order to create it and then store it. And so the first important piece is you have to have a geologic rock that has a high carbon content. Okay, so that's called a source rock. And a source rock, step back. Here are the oil reserves, and this just shows what countries sort of hold the oil reserves right now. And what's really interesting is you can see third down is Alberta, which is not a country, it's a province. But the important piece is that's all the oil sands right there. That Alberta is not really oil that you could pump from the ground. It's all in the oil sands. So it's a huge reserve of potential fossil fuel. And so if you look again at the world and where the reserves are, you can see Canada's got a huge bubble. The only reason Canada has that huge bubble is because of the Athabasca tar sands. If you took those sands away, their reserves would go down significantly. All right, now we can talk about petroleum geology. So petroleum geology is a small field of geology, or it depends. Sometimes it's a big field, sometimes it's a small field, depends on the price of oil. But it studies the origin, the occurrence, the movement, the accumulation, and the exploration for fossil fuels, and specifically hydrocarbons. Okay, so that's just lumped under petroleum geology. So here's what you need if you're trying to produce fossil fuels. You need a source rock. And so A source rock is a sedimentary rock. It means it's made up of particulate matter that's deposited generally by either rivers or in oceans. And that's where the hydrocarbons, the carbon is actually coming from. And so source rocks have to be rich in organic matter. And that organic matter is usually algae or plankton, phytoplankton that live in the oceans. They die. The organic matter that they've accumulated falls to the bottom of the ocean and accumulates there. And as long as it's not oxidized, it will remain as a fossil fuel source. So usually you need pretty deep oceans in order to trap that organic matter and create these source rocks. And if you have a rock that is like 1% organic matter, that's a pretty good source rock. Okay, so it doesn't take much organic matter, but it does take some organic matter to make these source rocks. And you can have rocks that have up to 10% organic matter in them. And sometimes when you see those rocks, they're just like oozing with oil. Again, usually deposited in deep oceans, lakes, or deltas. They tend to be really fine-grained rocks like shales or limestones if you're in the ocean. And not so much sands, because sands sort of imply a current, and if you have a current, that usually has oxygen associated with it, and it breaks down the organic matter. So you have to find a place where there isn't any current, usually the deep ocean, where all this plankton that dies accumulates over thousands and millions of years. All right. So once you have a source rock, a source of this carbon, and you got to remember where the carbon's coming from. The carbon's coming, anyone know where's the carbon coming from? It's going to the source rock, but where's it coming from? What? Okay, but where's the plants getting the carbon? Let's go to the... Where do they get it? The atmosphere. Yeah, they get their energy. Yeah, they have to photosynthesize, right? And so they photosynthesize. They pull in carbon from the atmosphere, CO2 from the atmosphere, and they use sunlight to create their structures. So what they're doing is they're pulling CO2 out of the atmosphere, and that CO2 is their carbon. And then when it gets deposited as a source rock, that carbon is now pretty much removed from the atmosphere. So over time, the accumulation of source rocks is actually decreasing the CO2 content in the atmosphere. And so when we go out and mine it and burn it, we do just the opposite, where we take that carbon that's been sitting in the rocks for hundreds of millions of years, and we burn it, and suddenly, that carbon that's been trapped is back in the atmosphere. And so that's sort of the cycle, but you got to realize that it's been trapped, it's been sequestered for hundreds of millions of years. So
that oil that you said moves out of the rocks,
yeah.
is that toxic then, as it's coming out of those rocks too?
That's a really good question. Yes. In other words, there's an awful lot of, so when you talk about oil, it's a mess of different organic compounds. Some of them are very toxic, because if you go out and get crude oil, that includes things like benzene and toluene and all sorts of toxic and carcinogenic organic molecules, as well as sort of the crude oil that we refine into gasoline. So when you talk about oil, it's a wild mixture of stuff. It sort of all depends on what was originally accumulated, how it was converted to oil. And so, yeah, if you find a rock that's oozing hydrocarbons, there's probably some stuff in there that's toxic. Like the sample that's being passed around, that Athabasca tar sand, you smell it. I mean, it's not going to hurt you to smell it, but you wouldn't want to smell that all the time, right? Yeah. Question? Okay. So we got source rocks. So we got the source rocks down there. Then you also need a reservoir rock, because the source rocks tend to be shales and limestones, and it's really hard to put a well into shale and limestone and pump anything out because it's too fine grained. Nothing flows through them. So generally, petroleum has to have a source rock, be converted to oil, migrate into what's called a reservoir rock. So a reservoir rock, here's examples of source rock. So there's a couple pictures. There's source rock from the North Sea. The North Sea has a big oil field. So that's 150 million year old black shales from the north. Actually, it's from Norway because it's not in the North Sea. And then in Pennsylvania, there was a lot of oil deposits, and Pennsylvania has these black shales, and those are the source rocks there. Then we go to the reservoir rock. So the organic matter, all the organic material is converted to oil in the source rock, and it takes a special process to convert organic matter to oil, which I'll talk about in a minute. But once it's converted to oil, the oil tends to migrate up. It's less dense than the rock, so it wants to migrate to the surface. So oil will slowly migrate out of the source rock, and if there's a rock with a high permeability, in other words, something that has lots of interconnected space, it will tend to accumulate there. And that would be the source, or the reservoir rock. And I think I have an example. Yeah. So this is sort of examples of reservoir rocks. Something like a sandstone with lots of pore space. The oil gets in there. A sand can hold a lot of oil, and the oil can move around in the sandstone very easily, which means if you put a well in and start to pump it, the oil can move through the reservoir rock into your oil well. So not only do you need the source rock, you need some sort of a reservoir rock to extract it from. There's an example of a reservoir rock from Kentucky, and you can actually see the oil oozing out of the reservoir rock, right? And then the other thing you'll need is, yep.
Is the reservoir rock something that's common to all oil fields?
No.
Or just the tar sand?
No, it's okay, good. It's common if you're going, let's see if I'll step back and say, you need it if you're going to pump it. In other words, if you're going to pump oil out, you have to have a reservoir rock. If there is no reservoir rock, then the oil may be either trapped in the source rock, and it's very hard to get out unless you start fracking. But I'm not even going to get into fracking. But it has nothing to do really with the tar sands. Okay? The seal, because the oil wants to move to the surface, you also need something to seal it in the reservoir. Okay? And so there has to be some sort of a cap that's impermeable for the oil. And that's usually another shale or fine-grained deposit. There's an awful lot of fossil fuel that we have lost in the past millions and millions of years to the atmosphere because there's no seal. So that oil slowly moved to the surface. Eventually it gets to the surface. Once it's at the surface, microorganisms will break it down into gas. And so there are actually places you can go and find oil seeps. So that's where there is no cap rock. The oil's being produced, it's moving to the surface, and in some places it gets all the way to the surface. One example of that is in Santa Barbara. Santa Barbara offshore has a large oil deposit, and the oil comes up, it's not trapped, and they're natural seeps, and so you get tar balls on the beach. Okay? And those are natural. Some of them are not. Some are spills, but some of them are just natural seeps that come up. The tar just slowly decays. So to hold in petroleum oil, you need the source rock, the reservoir rock, and some sort of a seal. Then the maturation process. I want to come back to this. Because that organic matter, if it was deposited a few years ago, it would not be oil. Because it takes certain conditions to take organic matter like dead algae and convert it to oil. And so the conditions are you need to have heat, and the deeper you go underground, the hotter it gets. Okay? So usually what you need to do is you have to bury that rock for long periods of time. And there's what's called the oil maturation window, which means the oil or that organic matter has to sit in an area under the ground, which is somewhere between 60 and 120 degrees Celsius. That's about 2 to 4 kilometers underground for millions of years. And that heat and pressure convert the organic matter into oil. So that's the maturation process. So it takes time to make oil. And if you heat it even more, it'll break the oil down into gas. So the gas window is 3 to 6 kilometers down. The oil window's 2 to 4 kilometers down. So if you have a large gas deposit underground, it usually means it was an oil deposit, but it got heated so much that the oil molecules broke down to much smaller gas molecules. So in order to make oil or fossil fuels, you need certain geologic conditions, but you also need heat and time. So here are the things you need. You need, and so you're almost lucky to make fossil fuel because all these conditions have to be there. If they aren't, you don't accumulate fossil fuel. So you need the source rock, the reservoir rock, a seal, and conditions for maturation. Okay, so let's shift our gears and look at the Athabasca. I'm going to probably going back and forth between Athabasca and Alberta oil sands, but they're pretty much the same thing. Because they're really unusual. And in fact, geologists aren't quite sure how they formed. Okay, so they have two competing theories, and we'll get to that. So I know you've been learning about the Alberta Tar Sands, or oil sands, and they're located in Alberta. And there are actually three major fields. One, or the biggest one, is the Athabasca field, which is that really large one off on the east side. And then there are two smaller ones, Peace River and Cold Lake deposits, that are just sort of adjacent to that. But they've all formed the same way. They formed from the same material. They're just separated because parts of the land between them have eroded away. So that's the location, right smack dab in the middle of the plains. And the Athabasca River sort of goes right through there. So that's their location. So they're unusual because they're really what you'd call bituminous sands. And bituminous sands are made up of bitumen, which is like the heaviest, stickiest oil out there. It's sort of like asphalt. You could almost compare it to asphalt. There's some really heavy sands or oils also in Venezuela, very similar. But the extent of the ones in Alberta are pretty unusual. So this bituminous sand consists of bitumen, which is actually soluble, water soluble. It's organic matter. It tends to be solid at room temperature. So if you saw this, you can see it's not flowing. It's solid at room temperature, but if you heat it up, if we heated this up, it would start to flow. It lowers its viscosity, and it flows a little. And then, unlike conventional oil, which you can pump out of the ground, you can't pump bitumen. It's too solid. So you have to find ways of extract it that are a little bit different. And it's also called asphalt. It's called tar sands. Sometimes you hear it called tar sands. Again, it's really sticky, doesn't flow, nearly as solid. So the origin, I said there are two theories. So the origin is sort of controversial. One theory is that the Bituminous Sands used to be a huge oil deposit, monstrous oil deposit, but the oil has been converted to bitumen probably because of microbial activity. So microbes got in there, destroyed the oil, and what you got left behind was bitumen. So that was one theory. And the other theory is there's some source rock deep down in the earth that produced the bitumen, and then the pressure of the earth squeezed it up somehow into the sands. So that's the second theory. And I was checking, and no one's come up and definitively proven it was one or the other. So we aren't sure exactly how the bitumen got into the sands in Alberta, but it's there. And so now I'm going to talk about how they go about extracting it, which is, yep.
I read once that the mines in the Athabasca area study the sand, the formation of land in Appalachia, because they believe some type of movement from Appalachia to this area took place at some point. Have you ever heard of that?
I've never heard that. You mean movement? I mean, like, it may, well, let's see. I was going to say it was, I mean, the sands themselves are 140 million years old, so they're much younger than the Appalachians. The Appalachians are much older. So I haven't heard that.
Okay.
I don't know, Dan. So there are two ways they extract it. They can't extract it by well. They can't frack, they can't do anything like that. So it's a very unusual extraction method, and we'll talk about the cost of extraction because it's really high. The two methods are either in situ, that means getting it out in place, or excavating it, and that's just digging it out of the ground. And so in situ involves what's called steam assist gravity drainage. And that involves, I said that when you heat it up, it becomes a little less viscous and can run. And so one way of extracting this bitumen out of the oil sands is to put in two horizontal wells, pump steam into the upper one, high pressure steam and water, and that steam and water heats up the bitumen, makes it a little bit more mobile, and then you can pump it out with an extraction well. So this is sort of a diagram of what it looks like. You got steam injection going on, and then you have an oil extractor below. Okay. Since most of the sands are too deep to excavate, like 80% of the sands are probably too deep to do open pit mining for. This is the process if they continue to extract bitumen from the Athabasca sands. they'll probably be using the in situ method because it's the only way they can get deep down.
Which is the most damaging?
Well, I would say that excavation is more damaging because you have more waste product. I mean, in this, you don't have as much. I'm not saying you don't have any waste, but you don't have as much waste product.
Do you have tailing ponds?
No, no, and that's a huge advantage. But it's also more energy intensive to get out. So, and then the other method, which is the one you see because it's so obvious, is just open pit mining. So in the shallower material where it's economically feasible to actually excavate it, put it in big trucks, truck it to refineries, that's what they're doing. So once they excavate the material, again, they have to get the bitumen off the sands and the shales. And so they take these truckloads of material into a processing plant. They usually add some chemicals to help the process, but then they also, again, have to use a lot of heat, hot water. They mix it around until the bitumen comes off the particles, and then once they do that, they can collect the bitumen. But going back to your question, then you end up with all these tailings. You have contaminated hot water, you have the sand and the shale that still has bitumen on it, and you have to deal with that. And so that's where those huge mine tailing ponds come from. It's from the extraction method. So
Things just sit there forever, don't they? There's nothing
now we won't say forever. Nothing's forever when you're talking to a geologist, but yeah, they do. You're right. Absolutely. It's, they talk about, I mean, in fact, they're required to go back to the open pit mines and restore the habitat. They don't quite do that, I don't think. But it's still, what you're doing is you're taking material that is already somewhat toxic, the bitumen, you're adding additional chemicals to it in order to help the extraction process, and so you end up with this slurry of toxic material that you have to do something with. And so usually what they're doing is putting in lined or unlined tailings ponds and waiting for the water to evaporate in order to condense the material. So
But then it's open and
it's absolutely open. Yeah. Yeah. Excavation. So the whole extraction process in terms of the excavation, which is most of what they're doing because it's cheaper, is they dig the open pit. They load up these massive 400-ton trucks. They truck it to the processing plant for extraction. They use a lot of heat and energy to extract the bitumen. Once they do that, then they can actually refine it into synthetic oils and things that we need. And then they also have the byproducts, which are the tailings.
who monitors the tailing?
Yeah, I mean, again, I am not an expert on the environmental policy, but